So let's see what we have. This first page, I hit an F5. We come up here. We got review. We got the purple line. You know what the purple line means. It means that we didn't go past it. And then we have backpropagation, which we did kind of go past it, but it's not on the test. There's some stuff about backpropagation that is on the test, and it's in the review slides. So when we get to it, you'll know what it is. All right, everybody good? You see, so I click on review, and there it is. You might think it's a year, but it's a course. And so what I just did is I grabbed selected slides throughout that said interesting things. All right, so this slide says what is the software of a neural net, and the software comes 100% from the weights. Oh, and let me say one more thing before we go on. This is where, if you don't understand what I'm saying, you say something, and if you don't say something, then I don't have to feel bad failing you. You get how this works? All right. So you got our neural net down there. The structure. Maybe if we're doing, if we're learning languages, you know, to understand natural languages and to talk, we might have a different neural net structure than if we're learning to recognize images, because they're focused on different sort of things, right? But we're not worrying about the nuances of the structure. The point is that if what you're doing is you're recognizing images, before you even know whether you're looking at images of frogs or images of bicycles, it doesn't matter, or images of cancer tumors, it doesn't matter, right? We're going to have the same structure here, right? You go to Google's thing and you say, I'm doing images, it will give you this structure, right? Then what's the software? What is the weights? And where do the weights come from? Well, they're too hard to understand, and we generate them with gradient descent. We learn them. Everybody good? All right. Which to me is magic. All right. What else do we know? I see a parallel between evolution and neural nets. And what's the parallel is that we're just bumbling along. We're in some state, and then there's some encouragement. There's some randomness happening, and there's some encouragement to go in a particular direction. And for evolution, the encouragement is, you know, some sort of survival of the fittest, right? And for neural nets, there's a supervisor saying, it's a face, it's not a face, right? And somehow we evolve to something that's a miracle, right? Okay. Why do we use machine learning? It was all on one page, so maybe you would miss it. But machine learning does better than humans, than coding, when, yeah? Yeah.
There's also really just one slide on it.
Yeah.
What do we need to know about, just there's a random change, or do you go in
This isn't just about the genetic algorithm. To me, this is about machine learning as a general thing. You know, hill climbing. Not hill climbing, gradient descent. Right? I'm standing somewhere. I have particular weights. Right? I've evolved so far, and I get advice from the supervisor, and that gets me to take a little bit of a step, right? So this isn't a slide about the genetic algorithm. The genetic algorithm clearly is like the genetics, like evolution, but I think gradient descent is similar. We have this crazy error surface that we don't understand, right? And we don't know where to go. We're blind. We get these little nudges in a direction, right?
Because there was one slide on genetic algorithm.
There is one.
And then that actually wasn't covered. And like you covered it, but it wasn't recorded. So then I had no idea what to know.
All right. Well, I don't have it in the review slides, but it's really that when I was a grad student, back in mid '80s, it was something that was working, right? This hill climbing stuff wasn't working as well, right? They would get little problems to work, but the genetic algorithm worked better. And you're on genetic algorithm? Okay, well, let's do this question first. One question at a time is my motto, right? So, what were they doing? In fact, I was quite impressed then. There was a grad student who was then hired on at U of T. So really, even then, it was moving. He got these little beings, and all they knew is they knew the laws of physics, but they didn't know how to move their arms, right? There was a controller that was going to control them, but they didn't know how to set the weights on the controller, right? So they had to learn these weights, and the way they learned the weights is they randomly had a huge selection of possibilities of creatures. And then they took pairs of creatures and they married them together and crossed them a bit. And they took individual ones and they mutated them a bit. And then they threw away the ones that weren't working as well. Right? And they repeated. And then you watch this video, and the ones that were light moved just like grasshoppers, and the ones that were heavy moved just like elephants. And you might not be impressed by that now, but I assure you in the mid-'80s we were impressed. All right? So that's that question. You had a question. Yes? Who?
I was going to ask, if it's not on the review slides, if it's not on the review slides, is it a test?
Yes, everything is on the test. I just randomly went through and grabbed things on the from here, right? So yes, there are things on the test that aren't in the review slides. But I'll assure you, you should know the things in these slides. Yes. Uh-huh.
Press escape on the PowerPoint, please. Just on the keyboard, just press the escape button.
Escape.
Oh, it's on. Okay, it's good.
It's good?
The fan icon on the bottom right next to the time.
This one here?
Yeah. Okay, great.
We're good. All right, you guys keep on it. You guys keep on it. Everybody wants these review slides. So you just, every day, help me with this. I'm good at some things, and some things I can barely make it and find the classroom. I'm working on my absent-minded professor image. Yes? Sorry, what? Oh, I think I did. It counted down. I remember seeing the countdown. I think we're in 8 minutes in. But everybody, never feel shame to ask. And that thing where I ask you questions and you answer them, I'm bumbly and not going to get around to it. And if someone wants to spearhead it, put it on my phone, put it on their phones, we'll do it. All right? Everybody get this? Right, what is machine learning good at that humans aren't as good at? Well, I can talk, but I can't tell you how I talk. Right? I can't tell you how I listen. Right? So, and that's the big thing. And if I go to Mars, I don't want to go there. I can't breathe up there. Right? Those kind of things. Right? Or I want to get advertisement to 7 billion people, and I want them all to be unique. Right? Those are good things machine learning are good for. Some of these are going to make, some ways the world's going to be better because of these things. And there's a real danger that things are going to be worse. Right? So these are just the overview slides, right? We have machine learning where the supervisor is telling us things. So what is our data? Where does the data come from? Ideally, we sample. I bought 3 desserts from the woman down the way. I'm going to get fat, but what are we doing? All right, so when we want to learn about images, so we randomly select images, and we get grad students or we get people on the internet to say whether it's a cat or a dog, right? So each of these X's is an image, right? And it's a vector because you know it has a lot of pixels, thousands of pixels. The Y is not a vector because it just tells you whether it's a cat or a dog. Everybody good? Oh, and here we're kind of, it's a funny graph because you think of graphs in high school as this being a real number. Well, really this is an image, right? This says for every image, is it a cat or a dog, right? So it's a funny, we're kind of mixing math here, but it's hopefully you can, helps, right? All right, then we have a machine. And at this point, we're not worrying too much about the nuances of the machine. What we care about the machine is that it's software. What it does depends on these weights. We have lots of weights, thousands and thousands of weights, right? And if you set the weights somehow, then it's a machine. And what does a machine do is you give it an input, which is an image, and hopefully what it returns is whether it is its best approximation, its best guess as to what the supervisor would give as an answer, right? So in this case, its output tells you should tell you whether it's a cat or a dog or a fish, right? Everybody good? And then when we have a particular weight, and I'm not putting in here the X's because I'm assuming the training data is fixed. We have a fixed set of training data. It's not changing. So now we construct this error surface. And what does the error surface say is for every possible weights, what is our error? So if we have given weights, we can say we know what the neural net does. So we can forward propagate and calculate what this neural net with these weights does on every training data. We know the answer to supervise, and that's this. That's what does our current weights do on the training data, right? And we know what the supervisor says for our training data. So the green line is what the machine says. The purple dot is what the supervisor says. The brown line is the difference between them, right? Yes? Yes. Yes. There are different error functions. And why am I doing this error function now? Well, I learned this error function early in my childhood. And it just feels the one we should do. And I don't completely get the negative log one. And it's a little harder, and I don't want to go that hard so right now. And it's the one that matches up with this picture.
So that can be used in this case? We're using that for neural nets?
Yeah. For this, if this is our picture, then this is the weights you want to use. Why? Because this picture is kind of saying y is a real value, right? And if y is a real value and being closer to that real value has meaning to you, then we subtract and we square. Yes?
Can you go over the
YD?
Yeah,
that's so given we have a given x, then here x5, right, is a certain image in our data set. We plug x5 into the machine, and it tells us that's the answer that the machine is giving. The machine's giving the answer 78. And however, the supervisor, the purple dot, is the y. The supervisor is saying, no, the answer not 28, it's 58. So we subtract the two, and say the error for the machine, it's off by 10. Right? And we're not going to care whether it's plus 10 or minus 10. And the bigger the number is, we want to punish it more. That's why we square it. So here is plus 10 or minus 10. You square it, and either way you get 100. And so why do we have a square? Well, because it makes it positive. As she said, it makes it positive. It makes it bigger, and it makes the math nicely curved. Right? Absolute values would be a disaster. Right? And then we sum up. That gives us our error for each data point. We sum up over all data points. Yes?
How does going through each of the hidden layers of the machine help?
You are on a completely different page. One of the things that I'm stressed already is that the nature of the machine isn't in our discussion right now, right? And whether a human has a nose is not in discussion right now. What's in discussion is that you change the weights on the machine and the answer will change, right? And we want to know the relationship between what are the weights on the machine and what is the error of the machine, right? So we're not considering the layers and we're not considering the hidden nodes right now. All we're considering is, given weights, how well does the constructed machine compare with the supervisor?
So this is basically like when you online, they give you those weird squiggly letters, and then you have to type in the answer. The machine, like, it's trying to tell you, hey, are you not a machine? It shows you a picture, and you type out.
Those things are called CAPTCHAs, and I was friends with a guy who invented them, and it has very little to do with this. Very little. Maybe if what you were trying to learn, given a CAPTCHA, what does it say, then you would get the world to give you the answers and you would plug it in here. But we don't care about whether you have nose. We don't care about the CAPTCHA problem. Yeah. No, I wouldn't. I'm not going there. Yes.
Okay, this might be kind of dumb, but shouldn't there only be a green dot for every purple dot? You know, for every input the supervisor gives an output.
Good.
Why does the machine give you a line?
Good question. Good question. And the reason it has a line is because this is a machine that doesn't know what the input should be. You give it something that's not an official data sample, training data, and it will still give you an answer, right? And so the green line is telling you what answer it will give on every possible input, whether or not it's training data. And why, in fact, I want to emphasize that because the purpose of machine learning is a sub-purpose is I want to get the right answer on the training data, right? But if your goal is just to get the right answer on the training data, then table lookup works really well, right? That's not our purpose. Our purpose is to go out into the world and not kill people, right? Or our purpose is to go out in the world and kill the right people. It depends on what your purpose is, right? So did that answer your question? Excellent. All right. So, we're pushing the button too hard. So everybody get this error function? Yes. Yes. Yes, what is the error? It's the sum over the training data of the difference for that training data. How wrong is that training data squared? In fact, I've never seen an error function that wasn't the sum over the training data. So that's kind of universal. And then you can plug in here anything that you wanted as an error function. The only thing we need it to be is kind of differential and smooth.
So with
Yeah. Yeah, you also add them up. There is you add up over all the training data of, you say, what probability, right? The machine is saying, the supervisor is saying that it's a bicycle. So we ignore all the other probabilities, and we say, machine, what answer do you give for bicycle? And we want that to be close to 1. And if you take a log of 1, you get 0. You take a log of 0.5, you get something that's negative. That's why we negate it.
For getting the errors, we don't care about the W0, right? The one intercept. Because when we had the regression line, there was W0, then XW1, XW2.
Yeah.
What happened to that, like the very initial wave that we talked about?
All right. So I will confess the slides have 3 ways that we have W's with indexes, right? Sometimes we're doing this picture with x1 through xn, and then we put w in. Sometimes we're going from node I to node j, and we do wij. Sometimes I have my big neuron thing, and I'm just labeling them w1 to wm. So those are 3 different ways of indexing or weights. And in terms of the w, you're talking about this w0, and yeah, because that's setting our threshold. It's a constant, and like I answered over there, you're talking about nuances of this machine, which I don't care about right now. Yes? This is the error function used for linear regression. Yes. It's the only error function I had ever seen prior to 6 months ago. All right, when I learned about in fact, I've only really seen 2 error functions, this negative log and sum of squares. Sum of squares is so standard in the world. All right? Everybody good with the error function? It's not on the test. What? I don't answer that question very often, so don't push me too hard. This function, everybody in the universe should know that this is your standard regression error function. You should know it. Yes. All right. Now we have an error function which says for every set of weights, what is the error, right? It defines some surface. For every weight, what is the height is the error. And our goal is to find the weights which minimize the error. So that's what this says. It says minimize the error, find me the weights that minimize the error, and what is the argument? I don't care about the actual error. What I care about is the weights that give me that error, and so that's the argument. Give me the argument that minimizes the error, and I'm going to call it the optimal weight. And calling it the optimal weight makes you think it's unique. It's not. There could be many weights that give you the same error. Everybody get that? It's the goal. Can we achieve this when we're doing linear regression? When we're doing linear regression. Yes. When I was in my first work term at a hospital, they wanted to know what is the best circle to fit the data. And I did bang, bang, bang. I did some calculus, and there I gave it to them. Right? So yes, if you're doing linear regression, this is easy. And if you're doing neural nets, it is not easy. Right? So, in general, we can't just look around and find the minimum. Right? It's a crazy surface with lots of valleys and hills and weird things. And to make it worse, it's a 1,000-dimensional space. Right? It's one thing to imagine hills and valleys in 2 dimensions, 3 dimensions, but in 1,000 dimensions, it's a little wonky. All right? So we use gradient descent. This is just answering a question that 2 people asked, which is, tell me the nuances of noses, tell me the little details of your neural net, and what I'm saying here is I don't care right now. What I'm saying works no matter what your computational problem is, no matter what your neural net is. Yes?
Can you say the optimal weight is like a local, it's a local variable?
If your hill's like this, we call this a global minimum. We call this a local minimum. No, when I say minimum, I mean this. Right? Yeah, so there might be a plateau here in which there are a couple of them, or maybe there's another valley that has the same height. Yeah, optimal is things that reach the bottom of the board. Right? What are we going to find? We're going to find these. Right? We're going to find local. Right? So what? Everybody good with this slide? Right? It says don't talk about the details of the machine and noses. Right? All right, so this slide, as I will tell you a little thing, is I kind of get excited about this slide, right? And you should know what your professor gets excited about, right? Why am I excited about it? It's because it's sort of where the magic, part of the magic is happening here. It's what's the goal of machine learning is not to be able to answer back, mimic back what the supervisor has told you. The goal is to generalize to other data. All right? So what is this graph? Well, this axis says how complex is your machine? Right? Are you doing linear regression, or do you have some crazy neural net? Or do you have some other type of machine? Right? And somehow we're measuring the complexity of the machine. And so what we're going to measure is how many numbers describe the machine. That's one measure of how complex it is. Right? How many weights are there? Yes? How many weights? In this case, yeah. How many weights? How many parameters?
But then aren't the weights determined by the neurons in the hidden layer, so you kind of want to have a bit less than the weight of the neurons in the hidden layer? Right? The number of weights is determined by how many neurons you have, right?
Right.
So then and then later on you say that you want to have a lower complexity, so you want less weights in the neural net, right? I mean less neurons in the neural net.
I'm not really getting everything you're saying. So there are 2 ways in which we may move left to right here. The one is I first try to learn using linear regression that only has a few weights. I later try this machine that has more weights. Maybe I can utilize those weights in different ways. Maybe the hidden nodes aren't useful, so I try different models. But generally, I try different types of machines down here, right? And I'm just ranking them based on how many. Some of those weights might not be useful, but I don't know that. I don't know what's useful and not useful. But I'm just ranking the machines based on how many parameters it has. So that's one way of looking at this. Another way of looking at this is we can automatically move left and right by saying, all right, I'm going to give you a lot of weights, a lot of W's, but I'm going to force you to make each of them small, right? I'm going to look at the sum of squares of the weights. Maybe the complexity along here isn't the number of weights, but right, we could have the complexity be the number of weights, or it could be the sum of the weights. K, we use K for weights, squared. Right? This somehow tells you the complexity. I allow you to have bigger weights. It's more complex. But anyway, just work with me. We got some level of complexity here. Yes?
Yeah, I'm a little bit confused. When you say complexity, you're talking about like overfitting, underfitting.
Yeah, we haven't gotten there yet, but yes.
But the way I thought about it, I thought
it's the other direction. How many bits, how big does M have to be? How many M in order to describe your training data? Yeah, we're going to get that into a minute, right? But everybody get here. Let's just stick to this slide. What we got here is you can have a machine with more and more weights, and the more weights you have, the more power you have to remember things, right? I mean, remember the machine, think about it this way, is the machine has to learn stuff about the training data, right? And how does it learn it? It learns it by setting all these weights, right? And if I give you more weights, then you have more numbers to write down. Right? Each weight, the learning gets to write down a number. And what is it doing with that number? Somehow that number is remembering something about the training data, right? Here is our training data, x1, y1, right? I learn it. How do I learn it? If I set values for all my weights. And what are these weights doing? Everything I know about the training data is in these weights, right? So there's a relationship between how much can I learn about the training data and how many weights I have. If I have more weights, I can learn more things. Right? Does that help? Yeah?
Is it possible to have like more than one weight for one training data? You have two weights for one training data? Is it possible?
I don't think you're getting it. I don't. We have N training data, and somehow from those we learn M weights. No, I lied to you. We have D training data, and somehow we learn M weights.
Okay, but how related M and D are?
That's what this slide is all about. This slide is completely about relating M and D. All right? If you want to know what this slide about is we have D training data, and we have M things learning about that training data, and then we plot here, you do your best learning. You say, for this machine and this training data, you find the best weights, the optimal weights, and we plot how well does that machine do on the training data, and how well does it do on data it's never seen before. Yes?
Sorry, one more time. I just want to make sure I get it for the weight and M. So it's kind of like the complexity of the machine isn't determined about how many weights you have. You can have M or M plus weight, 1 plus weight, but it's the M or the complexity of the machine is determined by the sum of the weights and what value you get.
No, I gave you different answers. I was happy with this. So then you asked questions that made me talk. And what I said is that there are other measures of complexity. But let's not go there. Let's stick to what I said on the slide.
Oh, so it's just a number of weights.
There are choices here on how to measure complexity. And right now we're talking that one. And the reason I'm talking about it is, I don't know if you know about Shannon's entropy, but Shannon was brilliant and talked about how much can I learn from n bits of information. And in fact, do you know how much you can learn from n bits of information? N bits of information, right? That's what it seems obvious, but from n bits of information, you can learn n bits of information. It's like something you can measure and hold in your hand, right? So here, this is like D bits of information, right? And this is M bits of information. Yes?
So it's how much you're learning, but you can apply that knowledge, like the learning, more, right? Than then. Because if it wasn't, then you would just always be only able to answer the training data. You wouldn't be able to learn faster.
I don't understand your. I sympathize that you don't understand anything I said because I don't understand what you're saying.
No, so you're saying there's n, you can learn n things from n bits of training data.
Yeah.
But then to apply those n things, you could have to be able to apply them more because or else it would just be, you would only be able to do table lookup with those n things. You wouldn't be able to learn past it. Because what you're saying sounds like you can't learn more.
If I want to learn the training data is made up actually not of d bits. It's because remember the images are thousands of bits. So it's a little wishy-washy here. I'm not saying it's complete, but I'm trying to parallel here. We have some number of bits to learn the training data. And then there's so many. In fact, we really need to learn the y's, right? So there's d y's we have to learn. How big does your machine have to be to learn it? To learn it, you need at least d numbers to learn it. If that's your goal, is to learn it, and there's no pattern here, Shannon tells you to learn d bits of random information, you need to know d bits of information. So if you want to learn this, m has to be bigger than d. Right? And what the 2 slides from now says, if m is bigger than d, you are able to learn this. And any learning program, any machine of any validity whatsoever would be able to learn that. Right? Polynomials of degree d. If you have d points, you can fit a polynomial of degree to it perfectly. Right? If you give me d training data, I could build you a machine learning machine that memorizes the answers. Right? I could build you that machine. Right? It's table lookup. So there's a relationship between these two numbers. And everybody understand those two numbers? Now let's talk about the relationship between those two numbers. Right? The first relationship is that if your machine's not complex enough, it can't do anything. Right? That's underfitting. It just doesn't have enough degrees of freedom, enough numbers to so it can learn anything useful about your data. Right? Your data down here, remember your data is thousands of images of cats and dogs. Come on. You got to learn something about cats and dogs or you're not going to do it. Right? And this is why in the 80s these things didn't work. They didn't have enough anything to be able to know what a cat was. Right? And then now we go over to the other extreme. Overfitting. I make this really, really big, and what's the machine going to do? It says, I am a powerful machine. You want me to learn your training data? I will learn your training data. And it does. Right? The error for the training data is 0. It learns your training data. Right? But it has no insight into the world. Right? So it doesn't generalize well, right? It's doing this. It's fitting the curve perfectly, but doesn't get the nuance of, hey, there's it doesn't understand things, right? And you might say, well, interpolating between this and this is as good as this curve between this and this. You might say that, but you have to remember, we got a 1,000-dimensional space here, and it's not as pretty as this. Right? Everybody get what I'm saying? All right, so where's our hope coming from? Our hope is coming from the middle. And in the middle, the amount of numbers we have, and M isn't well defined, and D isn't well defined in terms of bits. So don't take what I'm saying here literally. Right? But the intuition is we want just a little less. Right? It's less. We don't have enough power to memorize the answers, right? We have enough power to kind of get a feel for what a cat it looks like, but not enough power to know that that cat is Spot, right? And in order to, now it's trying to get as much out of this as it can. So now what does it learn? It learns that faces have noses. It doesn't learn that's Bob's nose, right? Yep.
So then, as like for human brains, is it all compression only, or is there?
Nobody understands brains. I certainly don't. Yes.
I don't think we're going to get through all the slides.
Oh dear.
Do you think maybe the last 15 minutes you can answer questions, and then also can we eventually skip to backpropagation?
We're not doing about. I have one slide on what you should know about. You should know it.
Yeah. So it's on.
Let's go faster. Yeah.
Here you say M is a bit smaller than
Yeah.
but earlier you said for a machine to learn it needs to be M bigger than
Yes. Both of those true. If you want to be over here, if you want to learn that Bob's nose has hairs in it, then you need to know every detail down here, and you need to know, and you need M to be bigger than D. If you just generally want to have a sense of what noses are, and you don't know, is that Bob's nose or is that Mary's nose, then it's okay for M to be smaller, right? And the advantage is that we don't care about Bob's nose. We want to know, what does a new nose look like? So we don't let it learn the details of Bob's nose. We only let it learn about noses, so that maybe, how did it manage to learn? How did it manage to learn all that data when it doesn't have enough numbers to write down? Somehow it must have understood the nuances of noses, right? It must have understood something, right? Just like these slides. These slides are a summary of all the slides. In order for me to make these slides and have them be useful slides, I had to really kind of understand the material pretty deeply, right? So then, hopefully, and this is just hopefully, this is all magic. We have, right? Hopefully it can generalize to new problems, right? Now, here's one theorem, and what is it saying? We're saying, when do we get a good answer for the general data, general inputs? When do we get a good answer? Well, it says a theorem, and there aren't that many theorems around. So this is one of the theorems. It says, if your M is a little bit smaller than D, and if you choose your training data randomly, and there is a good answer if the for the training data, and you find a good answer for the training data, then that training data, then that answer will work good for the general thing, right? There are a bunch of ifs there. If you check off the 3 ifs, then it works. Yes.
What's the epsilon?
It's a theorem. You plug in whatever you want. Epsilon's a little number.
Small number.
Yeah, 0.01. Right? It's as soon as you do math, you have to plug in numbers. Yes?
What do you mean by a good machine?
We're measuring our machine to be good if it's what percentage of the training data or what percentage of the general inputs does it get the right answer for. Right? So here I'm saying it either gets the right answer or it doesn't. It labels it as a dog when it's a dog. That's right.
So is it always choosing the overfitting? Overfitting always to the 100%.
Yes, but we're in the middle now. We're in the middle. Right? We're saying we don't have enough data. We don't have enough power in our machine to memorize the training data. That's condition 1. Condition 2 is that we did find a good machine that works for the training data. And, condition 2, was that the training data was chosen randomly. Then the conclusion is with high probability, it will also be reasonably good for the general inputs. All right? Everybody get what I would like for you all to have is some appreciation for what the statement of this theorem, and I'll tell you, the proof's not on the test. Yes?
For the underfitting, the error is huge, right? And for the overfitting, the error is huge.
So where does this break down? For underfitting, you can't do well in the training data. For overfitting, this is not true, and so when this is not true, we have a zero answer for the training data, and we have a very bad answer for general, right? That's saying you break this, you keep this, then this fails.
So a good machine is the one with an alright error on the general data?
Good machine, it's just what it says here, i.e. it works on all but epsilon fraction of the data, training data. All right, we're not going to move fast if we move slow. That was a good statement, wasn't it? Sometimes I impress myself. All right, so we haven't talked about specifics of machines yet. So we can. What is a neural net? It's these layers, and neurons either fire or they don't fire, and they have weights in between, which say, when this one, here's their weights. These are either firing or not. We want this to be either firing or not, or some half firing, because we're doing everything is real numbers, since integers scare us, right? Then integers aren't smooth, right? You can't differentiate integers. So what do? What is a neuron? Is we take a linear weight of the firings. It means we take this firing times its weight, this firing times this weight, we add them up. This weight here is a constant. It sets our threshold, right? And that gives us a number. A number says, how much do I want to fire, right? And what do we do with that number? We feed it into a sigmoid function, which turns it into pseudo-binary, right? That's our neuron. You have enough pressure, I'm a neuron, these guys, my friends are firing at me. If enough of them fire, I fire, right? What do we have here is just an example I got through here, right? We have two wires coming in, x1 and x2. So our linear sum has three weights because it has the constant, right? And what do we want to learn? We want to learn the AND function. So here, if you have two inputs, there are four possible settings. 0, 0, 0, 1, 1, 0, 1, 1, right? This one is yes, the others are no. What do we want to find? We want to find a linear function such that we call it a linear separator. Everybody on this side of the line, well, most of the people on this side of the line, we want to be no's. Most of the people on this side, we want to be yeses. Right? Everybody got that? Yeah? Let me tell you what I think people know. I think that the A+ people should know everything about these formulas and how to take their derivatives and how to play with them. And I think a passing student should be able to plot the sigmoid function and know that if it's negative, if z is negative, right? In fact, it's on the next slide, I think. What should you know? You should know that if z's negative, then it's returning 0. And if z's positive, it's returning 1. And it's nice and smooth in between. Right? To pass, you need to know that. Right? Everybody good with that?
A+ students need to know, always how to say the format.
Your goal is to learn as much as you can because it's going to get you a job. Right? What? I was just looking at another page. I read the science blog. And on the science blog yesterday was the list of the top 27 jobs which will not exist in 5 years. Right? This really is about getting you a job. All right? So if you go to Google and want a job doing neural nets, you should know this formula. Now that I've completely bashed you to the ground, any more questions?
Yeah. About the x1, x2 stuff at the bottom.
Yeah.
So we say the weight is -3.
Yeah, we have weights, and if you plug these weights into this equation, you'll get these numbers.
So that one weight applies to both x1 and x2.
These are our weights. The weights are independent of the input.
Okay.
Right? I fixed the weights so that if the green are the weights, the input is in purple. So you plug the input into the machine, and it gives you this Z value.
Okay.
If what you want to do is to get Y. So how do you get Y? You just put it in a threshold, the yes, is it positive, is it negative threshold, and it gives you the correct answer. Right? But we don't know how to learn thresholds because they're too binary. They don't have derivatives. So we add a derivative, and then what you get things that are sort of close to 1 and sort of close to 0. That's our sigmoid. And then you have some error. So you calculate the error how? You subtract the difference between the m and the y, and you square it, and you add it up, and you get some error.
If you use that other function remember there's another one other than sigmoid that works better?
There's the rectifier. Yeah, do I understand? Let's not get into the nuances of sigmoids versus rectifiers, right? We're not getting there right now. Yes?
So -1 means W1 X1 is -101.
You know I didn't hear a word you said. You know I didn't.
I mean, sorry, W0 is -3.
Yes, it's here, -3.
But W1 X1 is -1, right?
Plug in these, just calculate. This is high school. I have some values for W, I have some value for X, calculate what Z is. You can do, I'm not doing high school here. Yeah? Yeah, I take the difference, this minus this. It represents this minus this squared. You're asking, what does this, how do I feel about 0.22? Is it good or is it bad? We want to minimize, that's why I said we don't care what the error is, we just want to minimize it. Right? These numbers, none of these numbers mean anything to anybody. Right? They just want it to work. Right? And these are just one little table. Imagine you have thousands and thousands of weights and thousands of training data, and you're looking at this on your computer, and you're a poor grad student, and you're saying, what do all these numbers mean? They don't know what they mean. Yes?
With the threshold, could you understand, did you set it to 0 and 1? Because we want all the negatives to be 0, right?
I wanted to have a linear, I wanted to separate with a line.
But you didn't choose them 0 and 1 because it's binary. You chose them because with the way you make the weights, it's all going to be negative.
Yeah. What is a linear threshold? It's a line where we separate the yeses and the nos, and where should we use as a separator? 0 is a fine separator. We make the negatives, right? Whereas, it's not on these slides. What we do is we want to make these negatives, and we want to make these guys negative and these guys positive.
So let's say I make the weights so that anything under 5 would be...
But then you change the W0. I keep saying the W0 is to move the threshold. It moves the threshold from 5 to 0. That's what W0 is. The purpose, people are really obsessed with W0. right? The purpose of W0 is so that my linear threshold is thresholding at 0, right? Because I've built in what what my function is going to be, and my sigmoid function is thresholding at 0. And that's why we're learning. I don't want to tell the machine what it should threshold at. I give it a W0, then it can learn what the threshold at. Right? It's not for me to dictate. Why is it not for me to dictate? Because I don't understand. Right? Yes. Good. We are moving so fast. Hey, I'm really not cranky. I love you all. All right? So, here's the scary page. You should understand this page. It's when you read something about neural nets, they will not give you these equations. They will give you matrix equations. Right? So if you ever want to read a neural net paper, you need to be able to read matrix equations. And I've done my best here to tell you the matrix equations. I recommend that you learn them. Yes?
Should it xi and like the weights ij start from 0 because we have
Yes. Yes. And I have different notations for weights. And these and these notations, so these are notations where I'm going from the ith node to the jth node. It's completely different notation than when I'm talking about the ith input here, right? I know I try to uniform the notation, but sometimes we have to use the same letter. Yes?
Let's go make multiplication. Well, I'm going to ask this on behalf of class.
Yes.
Okay, so there was
In fact, there's no. Oh, here. Here's the. Where's the 0?
So there was
I don't.
matrix multiplication on our practice test, and even though I'm good enough at it to be able to write the math out, I wasn't able to answer it because the syntax machine in my head is different from the syntax machine in your head. I couldn't make a sentence that made sense with the 2 points.
If they were her, they were her. It's all her fault.
Please, even if there's only like one fill in the blank question and you have like a word bank with.
And the exam's gone to the printers.
Okay, is there a word bank? Like, I don't know because like, I can understand something and still not be able to fill it up.
No. I don't think you're getting. If you're saying, is there a word blank? I don't think you're getting my expectation levels, right? If I had you have a cheat sheet in which you wrote down everything on these review slides, then I would have to ask you something hard.
Okay, so then
Right?
if it's not exactly in the same word, but it's close enough for.
Hopefully the TAs will forgive you. But let me tell you something. When I've had TAs for 2001, they sometimes would ask me the dumbest questions. Right? They don't know what an exist is. Do they know what machine learning is? Hell no. Hell no, they don't know machine learning. Are they going to study it between now and marking this test? No. They're doing their own courses. Let's give them, they're striking. Oh, I sat on the subway with a charming mathematician who I know is involved in the union, and he went to the meeting, and the union goes, we want more money, but nobody wants to strike. All right. I personally, for the record, make too much money and I'm underworked. But don't tell anybody that. All right? All right, so we're going to get past this slide? All right. Now we're doing, it said gradient descent up here. No, yeah, we're doing gradient descent. What do we got? we're trying to find, what is our goal? You first should know the goal, is I want to find weights that minimize the error. How to do it? I start with some random weights. I find out where I am. I find the direction of steepest descent. I take a small step in that direction. That's the algorithm, right? People should know that we don't actually can see the error surface. So what's the slight difference? I know where I am. I know how to propagate forward to calculate the error of where I am. I know how to propagate back to calculate the direction of steepest descent. No, actually, we don't know how to back propagate, but we know that somebody does, right? Now we have a direction to head, and we head in that direction. And when do we stop? We could say you stop when you're at the bottom of the valley. What does that actually mean? You stop when it looks like every direction is up. Right? Yeah?
When you back propagate, you look for the direction of steepest descent and then go to back propagate.
Yes. Yes. All right. So, I made new slides, which are what I want you to know about back propagation. All right? This is a derivative. The goal of back propagation is to compute this for every weight. Right? It says last slides, but it was the last slides we were talking about it. I made these before. We know our current weights, right? What do we do? In our last, you should know how to do is you forward propagate to calculate your current error, right? And now for every weight, what do? You make a small change to that weight. You add, in our slides we added 1, but 1 could be a lot. We add just a little, an infinitesimal, right, to our current weight. And then you don't change any of the other weights, right? And you forward propagate again to get what the new error is, right? Here's the picture. We're only worrying about one weight. Here's my WK. Here's my WK plus delta WK. We calculate the error here. We calculate the error here. This distance is delta WK. This distance is change in error. You divide, right? You divide and you get the derivative, right? You should know what this means if you took calculus, right? If I change the weight, I want to know, what do I want to know? I want to know what influence does this weight have on the answers being right or wrong, right? And so how do I do it? I change the weight a little bit and see what effect it has on the error. Pretty straightforward. Yeah?
So you loop over K from 1 to n, but at the second line it says do not change attributes.
Yes. When I'm considering this weight, I don't change the other weights. When I go to the next weight, I go back, and these are done in parallel. Right? Then I go back to the previous value. I go in the other direction. Starting from here, I try this direction. I try this direction. Now, that's only 2 directions. Then I do my other 1,000 directions.
So you're actually finding the weight of each weight, right?
The influence of each weight. Yeah. What are we doing here? You should know what we're doing at least. We're calculating, if I'm here, what's my error? If I change this weight, then I'm here. Now what's my error? Right? What is the influence? What influence do I have on the error? Right? Do people care if I change something, right? Yeah.
At some point you calculated the length of the derivative. What was that?
Don't go there. Oh, I guess you could go there. What that was saying was, and I came up with that dreaming in dreamland. Question I have is, I know what the slope is in this direction. I know what the slope is in this direction. So which direction is steepest descent? it's say with ascent, it's the line in between. So what is the slope in that direction? And the math of how to do it, you're not going to know. Everything you need to know about, somebody asked, if it's not on these slides, do I need to know it? In terms of derivatives, everything you need to know is on these slides. All right? I know derivatives is pushing you all. All right? So this you need to know for derivatives and nothing else. Oh, and there might be another slide. All right, yes?
So it's basically you're looking at these different weights parallel, separate from each other, looking how much they influence the
Yes.
actual
Yes.
error.
Yes.
And
Yeah.
each time you check that, you change it.
Yeah. Let's say that we all had to decide when the next test was, right? We could do a game. We all have our opinion. We see when the next test is. Then we ask her to change her mind, and we see if the date of the test moves. Oh, it didn't move. We ask me to change my mind, and we see if the date moves. Oh, it did move. Which of us has more influence on the date? I do. Right? It's all about influence. Right? Everybody get that? All right. But do we do that for each weight? There are thousands of weights, and it takes us lots of time to calculate the error. We don't do that. What do we do instead? We do this magical back propagation, which is actually taking derivatives, and it's doing the chain rule, it's doing the product rule, and you could all do it. Right? But not today. So somebody asked me, this is not on the exam, on the midterm, will it be on the exam? So let me answer that. We're going to try to get through the course material and delete things that we think are useless. And if we have extra time, you can decide what we learn. And if what you want to learn is backpropagation, then it will be on the exam. And if you don't want to learn backpropagation, then it won't be on the exam. Right? Pretty straightforward. All right. So, this is the notation. You should also know this notation. Why? If you ever read anything on the internet about any of this stuff, it will use this notation. Do I like the notation? Not particularly. But it's the definition of the gradient. It says for each of these variables, what's the derivative of x with what's the derivative of v with respect to all of those variables? I never took high-dimensional calculus, and to give you credit, in calculus class we did x versus y, right? We didn't look at high-dimensional space. We didn't do partial derivatives. We didn't do vector calculus, right? So I wanted to know one day. I got obsessed with the orbit of the Earth around the sun, and I looked at the Wikipedia page, and I understood nothing. So I rewrote it. I went and I learned vector calculus, and I rewrote it. So now maybe you could read it. All right. So we learn all of these influences, and what do? Well, when it has a positive influence, we increase it. When it has a negative influence, we decrease it. Right? So what are we doing? This vector, for some weird reason, is the vector of greatest ascent. Ignore, that's supposed to be an ascent, right? It's going up. So what do? We change all our weights to go in the other direction. That's the negative, right? We take, how much do we change this weight? Well, we change it in this direction, proportional to that amount, by our step size. And what is our step size? It's some little number. Yeah. Because I spent, over my lunch, when I was doing, I did the math and I proved it. My son said, well, of course it is. And I didn't believe him, so I came up with 2 proofs that it was. We hand wave proofed it here. You can go through the hand wave proof here. With all those lines, and you want to go perpendicular to the lines, and that's the best I got for you. Yeah? But I'm glad that you don't see it's obvious, because it wasn't obvious to me. All right, back propagation, right? This was the picture, right? We had the derivative in this direction, the derivative in this direction, right? Here we have the derivative in this direction, we have the derivative in this direction, and for some reason, that's the direction of steepest ascent. You can sort of see it from the picture, but that's all I got for you. Everybody good?
So, in the first way that you said was too long, we were changing WK by a small value. And then when we were doing the back propagation for steepest descent, so we were reversing that equation, we were saying,
Don't let us make us learn calculus now.
I just mean one is minus and one is plus.
Is it? Then that's a typo. Where?
I'm not sure if it's a typo. Basically, it says WK plus delta.
Yeah. Yeah.
Yeah.
That's,
And the next slide, it's WK minus the step size times the error change in weight.
right. Let's look at that slide.
That's a new weight that we made, right?
So, here, it's here. Oh, why do I walk here to want to point at it? It's clearly higher than I am. Look at, there's a W on the top here and a W on the bottom here. It's completely messed up. And that's why he doesn't understand that this is direction of steepest ascent. That's why I don't understand it, right? On one side, I want to calculate the influence, which is, here I'm saying if I change W2 a little bit, I increase W2 a little bit, how much does it increase my error? That's one calculation. It's calculating the slope. And then, then somehow we get which is the direction of steepest ascent. And the direction to head is proportional to the slope. And there's some weirdness there, right? W here, down there, W here, it's a little weird. That's the weirdness that he doesn't understand. Now, why are we subtracting here? Is because here we were adding on the weight because we wanted to know positive influence here gives me positive influence here. Here we're subtracting the weight because this is steepest ascent and we want steepest descent. How are we doing for time? We have 5 minutes. What do you want to talk about in 5 minutes?
Two questions about Turing machines.
Excellent, excellent.
Is it good, like, because in some point you said Turing machine is not going to be on the test, and then
Oh, I never said that.
you said up to Turing machine. That's
Oh, yeah. Turing machines is...
So I don't get it when you say up to Turing machine. So Turing machine is going to be on the test.
Turing machine is so on the test.
Okay, but
So on
will
the
you tell
test.
us, like, until what slide number?
Well, were you at last class?
I wasn't here, no.
Oh, well, then we had a lengthy discussion, and I said not including last talk, but then periodically I would say things, and I'd say, oh, yeah, you should know that, oh, so you should know that. All right? So let me tell you, I can't give you page numbers, but I can tell you exactly what's going to be on the test. All right? I'm going to give you Java-like code which says, take the value that's at the head and store it into X. You're going to have to compile it into Turing machine code. Now, there are different levels of abstraction, and I want you to know all of the levels of abstraction. So at one level, I'm going to be looking, do you know that a Turing machine is only states, and I know what state I'm in, I know what character I'm looking at, so I go into another state. You need to know that, right? And then you need to add on the next level of abstraction in which I give the states meaningful names. And that allows me to say, well, when I'm in the state, what do I know? I know that X is 5, right? So that's another level of abstraction. And then the next level of abstraction is you want to be able to fill in the table a lot of the table. So I say X equals X prime, right? So when I say you compile it into Turing machine, it's that level of abstraction, right? you need to be able to say, I'm in state line equals 1, and I'm looking at a C, so now the state I'm in is line equals 2, and I have a value, a variable that's remembering that, right? And maybe here I knew x was an arbitrary value, and this is an arbitrary C, and so now x is remembering my arbitrary C. You need to know that, all right?
You have like these questions. How do we tell how many states is needed? 'Cause
You need to understand. What do you need to understand? You need to understand that if my state is line equals 1, and I'm remembering various value, this value is between 1 and 10, and this value is between 1 and 10, then I have 100 states of line 1. You need to know that.
yeah, but there's this question, I don't know where you read it, maybe you put it somewhere. That you're adding one digit, like one.
People can leave if they want, and you can keep asking questions. And then the other thing you need to know is first order logic. You need to be able to say for all exists, and it will be talking about Turing machines. Yes? The word multi-tape is on the exam. What do you need to know about it? You need to know that it exists as a concept. Yes? Yes, I just said that. What? Concept of multi-tape is on, you need that, the concept of a multi-tape is on the test. What do you need to know about it? I'm really sure you know what you need to know about it already. I'm really pretty sure. Yes.
So states depend on whatever the machine has to remember.
Yes.
Okay.
Yes.
So
all I know is what state I'm in.
So if you're adding the example you gave on the question on the forum, if you're adding 1, each time you only have to remember that one number. So there's only one state.
Yeah, that's what I don't get. Like, there you don't know what to memorize and what to not.
So it's
Oh,
like
you actually
you're-
memorize one digit every time, right?
You give a string of numbers, like
Yeah.
1, 2, 3, and you add 1 to each number.
Right.
So you only need to remember 1.
No, actually, I don't remember anything.
Oh, because
Right?
you just added.
I am completely stupid.
Oh, okay, you're just
I
adding.
know nothing. I grab the number. Now, Pooh Bear knows what state I'm in, which is nothing, and he knows what character he's looking at, so he can do anything based on what he knows. And what he knows is the state, which is nothing, in the character. He adds 1 to it, and he writes it.
Okay. So it would
And
be
then I
just-
go over here, and I know nothing.
Okay.
I have 1 state.
You need as many states as you have numbers.
No, there's an exponential thing there. If I have to remember X, Y, Z, and they're all between 0 and 10, how many states are there? There's whatever that is, 1,000 states, right? So it's not a 1-to-1 like you're saying.
And talking about level of abstraction, like, would you mind if you write all the states? Because you sometimes like skip some of the states, right? From line 2 you go to line 4. But
Yeah.
would you mind if you just write everything down? Because that makes more sense to like, it's easier to understand.
So I think what I'll tell the TA, maybe I'll come up with a number of answers, right? The answer where you do every step. If you want to pass, you should be able to do that. If you want to get an A+, you need to be able to do it all in one go.
Okay, but Turing machine, the multi-tape is not going to be on the
It is. I've said
Is
it.
it?
Oh, you weren't in the class.
No.
So
'Cause there's
let
a
me
lot of slides, that's why I'm so
okay.
confused.
Let
Like,
me tell you
one
what
makes
you need
sense.
to know about multi-tape. You ready?
Yep.
Multi-tape is like a single tape, but it has multiple tapes. There.
Yeah.
He knows everything he needs to know about multi-tapes. That's all you need to know.
Okay, but how much of these slides do we need to know? Like, it's 270
I told you,
slides.
you need to know it all.
Oh, yeah? Okay.
I'm telling you what's on the test. I told you what's on the test.
Got it.
Right? So it's a skill. You need to be able to go from here to here. What do you need to know about multi-tapes? I'm really serious. What you need to know about a single tape Turing machine is that it has a single tape. What do you need to know about a multi-tape? It's bigger and better because it has 3 tapes. You need to know that.
And even the converting them, like, do you want us in the test to convert them? Like from the two, like two tapes to one tape?
Listen to my words.
Gotcha.
Listen to my
I
words.
don't want to ask more questions. I don't want to get more confused. But yeah, now I know.
Yeah. When we were in class last time, I said one of the things that I wanted to delete from the course is converting from single to multi-tape. How many minutes did we spend on it? 3. We spent 3 minutes on it. How many minutes did I spend on it last term? An hour and a half.
Oh, that's I was listening to the video was from the last time.
Right?
So I'm confused.
All right, so
Yeah, okay.
I'm deleting out, what am I doing? I'm being an anarchist. I'm deleting out the hard esoteric things, and I'm replacing it with hard, non-esoteric machine learning.
Thanks.
That question that you posted on the forum, the 1, 2, 3, 4, 5,
Yeah.
the one that you add one.
Yeah.
How many states are there?
1.
And also this last slide, you said it was too hard, right? It took too long. But here, are you kind of doing the same thing with the delta E?
We're getting the same answers, but when we did it the other way, we had 10 to the 8 training data, weights. This is the number of weights, right? And for each weight, you calculate the error. And this takes you 10 to the 8 time. So you multiply that, and you get more time than you want to spend, right? So instead, we use matrix multiplication, and we come backwards, and we do them all together in this sweeping way. And instead of it taking 10 this times this, it takes more like this plus this. We're not covering it. So, yes.
Loop invariant.
Yes. What is a loop invariant? You need to know the code I'm going to give you will have a loop. And because it has a loop, it will have a loop invariant. And could you convert the code into Turing code without understanding what this code does? Yeah, you probably could. If you understood what this code does, will it make you warm and fuzzy and help you a little bit? Maybe. How do you understand this code? Do you know what the loop invariant is? And besides, what is the loop invariant? It's actually, I take it back. The loop invariant is very important. Because the loop invariant says, I'm at the top of the loop. What do I know? Right? What do I know at the top of the loop? I'm not looking at anything on the tape yet. What I know is what state I'm in. So I'll tell you what state you should be in when you're at the top of the loop. I'm in line, top of the loop, and I write down everything that loop invariant tells me that I know. Right? If it tells me that I know the value of x, y, and z, then that's what I know when I'm in the state at the top of the loop. Right? Does that make sense? No. No. Do we have an eraser? So, loop invariant. It's a statement at the top of the loop. It says, you are at the top of loop. Head is somewhere. X equals something. Y equals something. This is the loop invariant. It tells you what's true at the top of the loop. Right? Now, I'm trying to convert, to make Turing machine code. Right? So the very first thing I would say is, I know, where am I right now? I'm in some state. What do I know in this state? I know that I'm in the line at the top of the code. Oh, the head is somewhere. Can I put that in the state? No, the state doesn't know where the head is. Right? That's just for the use for outer people. Right? Oh, the state does know that x has a particular value. It does know that y has a particular value. Right? So, So now, I also give you code, right? Here's the loop, here's loop, and then we give you code, right? And what I recommend you doing is you look in this code to see where the head moves, right? Head moves here, it moves here, right? So I'm going to say this is, we change states whenever the head moves, right? So I'm now right here. I'm in line 0. I'm at the top of the loop. And I see the head moves here. All right? So now I'm going to say, where am I? What do I know here? I know this. Right? Okay, what is the Turing machine going to do? Well, the head hasn't moved in this whole length, right? Because the head's moving here. So this whole period, the head's one place, right? What character am I looking at? I'm looking at some character, right? And then, he didn't like doing all these lines of code, right? It made him nervous. But I'm saying, let's go from here all the way down to here. I'm in this state. I'm looking at this character. I haven't moved the head yet. I'm about to move the head. So I don't know where the head's going, right? But I know the value I'm looking at now, C. So I know everything I need to know in order to get down here, right? I know where I'm here. I learned nothing through here except for the C, right? So I know, this tells me everything I know here. This tells me the C that I'm reading. So I should be able to know what I know when I get here. Right? So I write it down. What I will know is that now, what line am I in? Well, if I'm here, maybe I'm in this was line 0 and now I'm in line 1, or maybe I've circled around and I'm still in line 0. Right? Depends if this is the bottom of the loop or not. Right? What line am I on next? All right, I'm on some line next, and I know things. Maybe I know now that x equals c plus the value of y prime. Right? Here I knew the value of x prime. Here I read the c, and so I can know the value of c plus x prime, and I know from the code, from this code here, that we say a equals c plus y prime, the value of y. Right? So
this is going to be your loop variant, right?
This is what do I know when I come back here. Here, I knew that x was 5 and y was 7. And I'm reading, out in the world here, I'm reading that c is 3. Right? And then I see this line of code that says x equals c plus y. So I know the value of c is 3. I know the value of y is 7. I add them together. I get it at 10. I know that what happens down here, what's y down here, x down here? X has this value. Right? Now what about y? Oh, it says, forget y. You didn't really need to know y. All right, I forgot y. I got no y. Right? What do I know now? I know I'm in a new line. I know the value of x. I forgot y. Okay, great. Now, I've collected everything I've learned. Now I know what's here, and I'm ready to move my head. I'm ready to move my head right. Oh, no, not completely, Red. I got to write something. Oh, did it say what to write? No. Maybe it did. Did it say what to write, or did it write x? Let's say, I was asking you to make it up. Let's write the value of x. Right, here we're writing x. Right, so here, before we know x prime, so we're going to write x prime out. Right? This says, I'm in this state, right here. When I'm right here, What do I know? I'm at the top of the loop. I tell you what you're supposed to know. I'm here. What do I know? I write this down. And what do? Is I read the head. I know what's in the head. Now this is what I know. So I'm going to know that until I move the head. Everything I know, I know. I'm never going to learn anything new. Right? I can do any math of what I know. What do we need to write down here? We need to write down, what am I going to memorize? What am I going to remember?
The value of x.
Right?
The old value of x.
I'm going to remember, and what am I going to write? And which way am I going to move the head? Right? So what am I going to remember on my blackboard is what's the line of code. The value x has this value. What am I going to write? I'm going to write the old value of x. And I move my head. And that gets me here. And now I'm ready to read a new character.
So we know we change the state when we move the head. When our head moves, we change the state.
What a Turing machine is, I'm in this state, I read this character, what's my next state? What character should I write? How do I move the head? That's the lowest level. Right? If we don't let you do stays, you could break this up until you stay a while. But the truth is you don't need to. The truth is, I know everything I know until when do I learn something new? Is when I move the head. Right? Now, what do I need my next line of code? I can pretty much copy this. Right? I say, now I'm in line equals 1, x equals some new value of x, and I don't know a y. Now I have a new value that I'm reading, right? And now I need to get, what do I calculate until I get down here, right?
I remember in one of the examples you had the loop variant at the beginning, and then the loop variant at the end changed.
I don't know. Loop invariant doesn't change. Loop invariant's at the top.
Like how many highs we write? You said first the loop invariant is the number of highs.
Yeah.
And then at the end you said that we have the loop invariant is 10 highs.
That's that.
Yeah, that was. Yeah, the loop invariant was the number, that some variable. We had some variable which r equals the number of highs. That's the loop invariant. And the exit condition is that r equals 10. And the post condition is that the number of highs equals 10. Right? So loop invariant plus exit condition gives me post condition. Right? Does that make sense?
No, I understand it more.
Excellent. You know the problem with these talks is we get new ways of saying it, and then I have to make more PowerPoint slides.
Oh, sorry.
Yeah. I do love making PowerPoint slides. It's all good.
So the direction of steepest ascent, because it's going up.
Yes.
It's going up.
Yes.
How do we know?
We don't know.
How do we know what? We calculate the derivatives, and that tells us the direction of steepest ascent. Sorry, that should be an ascent. And what do? We go in the opposite direction. We descend. What?
But what? So we have to go into the opposite direction.
Yes. Right, that's why we're subtracting.
In last part, for the Turing machine example, we gave that the head just moved, it looped, everything just one line. So when would I know, like so the Turing machine does in just in one line, or it will have different lines?
Well, that was
So when the
that was where, in the loop, I say, look where the head moves. And the head only moved once. Every iteration, the head moves once. And, between you and me, that's often the case. Right? It's often the case that the head moves once per iteration. Right? So, in that way, it's frequent that there's only one line. right? I know something. What do I, the typical loop is I know stuff from the loop invariant. I look at the head. Now I know this and this. Then I do lots of thinking. And then I write some value. And I remember something. And I move the head, and I go back up to the top. Right? So how do you translate that? He says, this is what do I know at the beginning? Right? I know that I'm at the beginning. I know these values. I read. Where did I read? Oh, there, somewhere. Oh, no, up here. You're at the, I lost what I'm doing. But I know something. I read the character. I do some math that tells me two things. It tells me what I'm going to remember afterwards, what I'm going to write afterwards. And then I move the head, and and I go back to the top of the loop. And you want to make sure that the loop invariant gets maintained, right? Or, in fact, you say, what do I need to know here so that I'm allowed to go back to the top of the loop? We got too much writing on top of each other.
So, for example, like we have 0, 1, and we have to reverse this, right?
Right.
For example, that's what our Turing machine does. So in this case, so I have to read this character and this character, and I have to know the length, and I have to know the length for this one and compare, right? For the string.
No, in this case,
So then we'd have more lines.
yeah, you need more lines because the head moves a few times.
So we know that
Right.
we have more lines, right?
In fact, yeah. So you had these instead. How many times does the head move? 1, 2, 3, 4, 5. Right? There are going to be 5 lines. There are going to be 5 lines per loop.
Okay, I just want to make sure the difference between
Right.
the one line execution.
Yeah. What do I know now? Nothing. What do I know now? The state knows nothing, but I'm reading a 0. What do I know now? I've remembered the 0, and I'm looking at the 1. What do I do? Write the 0, forget the 0, remember the 1. Then I come back. Write the 1, forget the 1. Now what do I know? Nothing. I come over here, I know nothing. I come over here, I know nothing. I'm ready to loop. Right? Does that make sense?
I just want to make sure that I haven't fallen in the trap. That
Yeah.
It's done just one line, or it's done just different
Yeah.
lines?
Yeah, you're right. This we have 5 lines.
Okay.
Okay. I get the Turing machine stuff. I get that.
Yes.
I get the
Excellent.
a lot of the order logic.
Excellent.
I did good in 1090. I think I can get that.
Excellent.
What I want to make sure.
Well, you know what I'm making you do in first order logic? A danger is to say, I understood 1090, so I'm not going to study what Jeff wants,
I know.
because Jeff wants something different.
Jeff wants you have the adversary and you have.
Meaning, I want meaning and I want the game.
Exactly. You want the game and you want actual understanding.
Understanding. Yes.
Something people can understand when they say it.
Yes.
Right. What I want to understand is the machine learning is just go from the top up here.
Did you understand what we did today?
I understood most of it.
Really?
I understood.
Why? It's so
It's more like
so easy.
It's not the fact that it's what you're in particular individually. What you're saying is easy. It's the difficulty is to understand what that you expect, and it's kind of unclear.
What I expect is that you get a job with Microsoft.
That is a statement that is clear, but that does not tell exactly what we need to know from the slide.
If you want to get a job at Microsoft, you need to know everything I'm doing here plus.
All right. So I'm just gonna state this.
Yeah.
You gotta know that there's 3 types of machine learning.
So if you want to pass this course, if you understand everything in the review slides, if you could dictate back to me the review slides, you will definitely get a B. If you want to get an A+, maybe there are nuances in the slides that you need to know. Right? Oh, I lied to you a little bit. There are some places in the review slides in which I said there are various things you should know, and you have to go back and look them up.
So before back propagation, we're not gonna deal with back propagation as you said on Monday on the test.
The derivatives is it's high school calculus, and we're not doing it. We're not doing it.
I just wanted to make sure, I wanted to be clear of what you say. It's one statement.
Slides. You need to know that derivative of E with respect to xk is our measure of influence. You know the influence, you know the meaning of the derivative. And I bet you if you were on a desert island and you had a month, you could figure out how to do backpropagation. It's just high school calculus.
I'm not worrying about the math. That's not
Okay.
what I'm worrying about. That's not my question. I just want to be clear on what exactly you want
Have I answered it the best I'm going to answer? Would you like me to give you a copy of the test?
No. It's just the way you're saying it is some things you say you're going to admit, some things you're putting in there, and then it gets confusing in the lines. And I'm trying to understand what does he want, and I think that's what
I'm going to sit down.
I think that's also your mic is still recording.
I know, because people were asking good questions, and our home audience is still listening.
Yeah, I'm sorry, but I just want to be clear. It's not the math.
You know the game. We have a game here, and the game is you're not supposed to know what's on the test because I want you to study more than what's on the test. That's the game.
So is it like all question answers, or do we have to follow the lines, or?
I told you already. I said already. They're all 1-2 sentence answers. I ask you a question, you give me 1 or 2 sentences. I ask you a question, you give me 1 or 2 sentences. And I swear to you, for each of those sentences, I could find a slide in which those sentences were written, and with a few exceptions, they're on the slides we looked at.
So, you've got to understand, for instance, with the epsilon n equals epsilon d. Epsilon is basically you're trying to find the minimum error between m and d, while also trying to make sure the minimum error between the general data and
Our goal is we drive around Google headquarters learning, and then we go out into the world and we hope we don't kill people. And how do we have any hope of not killing people when we go out in the world when in Google compounds we've never encountered snow before?
you've got to understand the gradient descent and back propagation and all that jazz.
No, that's about the theory of how we go from test data to general data. We want, the test data isn't going to know about everything, right? It looks at his nose and her nose. It doesn't look at your nose, right? And so we have to understand your nose from looking at their nose. And the truth is, I'm going to know the general shape of your nose, but I've never seen your color before, so you're not a face.
Exactly. So it's trying to say, basically trying to get the generalization, the universal idea of a
Yeah,
nose,
yeah.
instead of saying that particular.
Yeah,
nose.
exactly.
We're trying to understand universal.
Exactly. If I learn the nuances of his nose and the nuances of your nose, I'm going to be confused by your nose.
But you know the general idea of the nose,
General idea of his nose,
you'll get most
I
likely.
might get something from your nose. They don't know more than that. Right? Maybe the head at Microsoft knows more than that. I don't know more than that.
When you talk about data that's chosen with high probability,
No, the data is chosen randomly, and then we will get this with high probability.
okay. I just wanted to make sure
Yeah.
it wasn't like the data is.
No, it's saying if we choose it randomly, then with high probability we get this.
Okay.
Excellent.
something about first order logic.
Yes.
And you said something about like having a general idea of some concept, and I couldn't hear what you said. It's something to do with the test.
Well, I can tell you what's on the test. I don't know what I said then, but I can repeat what's on the test. If you want to get a B in machine learning, you need to understand the review slides. If you want to get an A+, and maybe even to get your B, in order to understand the review slides, you might have to refer back. Oh, what was he was saying something here. What was he saying? He was saying, maybe machine learning is useful in these cases. When is it useful? Go back and look. Right? That's what you need to know for machine learning. What do you need to know about Turing machines? You need to know that there's these levels of abstraction. You need how to convert from this code into that code. What do you need to know about first-order logic? You need to be able to understand what it's saying. And I came up with a whole new way of helping you with that. And I haven't made the slides yet. But remember, it was about, if you were in the class, we kind of, instead of reading from right to left, we were learning from left to right. And we focused on the free variables. I kind of like that, right? But anyway, somehow you have to get, what is this line meaning, right? And then you have to know the game. If it's an exist, then I construct it. If it's a for all, I say let it be arbitrary. If you know all of those things, you're good. That's the test.
I got it. So what you mean that means, so for your machine learning, not all of them will cover the test, the midterm, this test.
You do not need to know the derivative of the sigmoid function.
Yeah,
No, you don't.
We have to know all the logic one and the closement thing. It's cover all of them.
Essentially, now you can calculate error for any.
I'm sorry, I don't always understand what you say.
Like closing machine, I mean, it covers everything, all of them.
I'm not going to say anything that I haven't said already. I told you what was on the exam. You just have to stop asking me more.
Yeah, the thing is, the exam's going to be simple, but it's really scary.
Yeah,
It's going to be simple. We're just scared because we don't know what to expect.
do I think half of you are going to fail it? Half of you always fail it. Why do I think it's going to be any different? Do I think it's hard? No, it's not hard. Hey. Hey, I know you. Are you here to bother me? Oh, great. You know, I'm just so bothered these days. The world just feels like a big bother. And you're going to talk about